Hey everybody, this is Larry. This is me going with Q3 of the weekly contest 393, Cave Smartest Amount with the single denomination combination. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So this one, I'm gonna bring up the drawing pad real quick. This is something that you might not know, and if you haven't seen it before, it is one of those things. And to be honest, I've seen this, not this problem, but this idea before, and I actually forgot how to do it. I kind of rushed it a little bit, and I had to kind of reprove everything in my head, right? But basically, the idea here is that, okay, let's say we have 4 sets, right? So we have sets and sets representing as a big circle. So you have one. Maybe actually I could just use the. I don't need to draw circles. I could make perfect circles, right? Something like this, right? I think that is all the sets, but I could be, or with the intersections and stuff, right? And then the idea here is then, okay, well, you have to try to count how many numbers are there, or sorry, let's say, and this works for everything, right? In a way, let's say, I don't know, what is an intersection? Let's say we're talking about people, and this is the set of. What is I don't know. Let's say this is just tall people. You could define tall however you like. This is another attribute. I don't know. Long arms. I'm just looking at my arms, right? Right. And then maybe what am I doing? That is not that is safe for work. I don't know. Big legs, right? And then okay, maybe black hair, because I have black hair, right? Okay, so let's say you have these 4 sets of people, but the thing is that let's say we have 100 people in total, and of course, if maybe 3 people are tall, 5 people have black hair. I don't think this adds up, but 80 people have long arms and 70 people have big legs, right? Well, now the question is, okay, actually we don't know that it's 100 people. I forgot. I messed this up. Sorry. Let's say this is what we know. Well, how many people are there? Well, you don't know, right? Because as you can see from this Venn diagram, there you go. Some people with long arms could have big legs, right? Maybe let's say 40 people have both long arms and big legs, and then maybe you have how many people have both black hair and big legs? I don't know. Let's say 1 because I messed up the numbers. You get to my point. And how many people are tall and black hair? Also 1, right? And so you have all these things, right? So then now, what do we do with all these things? I mean, let's pretend there are numbers in all of them. The thing is that you can't just add up, you cannot just add 3 plus 80 plus 5 plus 70. And we all know this, right? Because like we said, there are, too many people. So then now we have to subtract out some intersections. So now you have to subtract out 40 because you know that we counted 40 people in the big legs and 40 people in the long arms, so we double counted these. So we minus 40, we minus 1, we minus 1, right, for the tall and bracket. But, and maybe, I don't know, just minus 2 here. But what happens, right? So then now, let's, I mean, the numbers don't matter that much for this particular one for now, but let me, let me change colors real quick. But then now, okay, let's say you have this. This is not what we're counting, right? This is actually what we're doing with 40. 40 is the number of people with long arms and big legs. But as you can see with this intersection, and okay, fine, right? With this intersection, now, when we subtract it out too much, right? Because there are people who have long arms, big legs, and black hair, but we subtracted them, so we have to add them back in. I have to change colors. So we have to add these numbers back in, for example, right? So you have to kind of do this. Why is this so the stroke thing change, right? So anyway, yeah. And then this is basically the idea, and that we're gonna go for this problem. It is the principle of inclusion-exclusion. Some people label it as pi for that reason, but I don't know. I just call it inclusion-exclusion. So you can Google this if you want to know more detail. And now let's think about what it means for numbers, right? So we'll use this one, 5 and 2, but I'll add another number, right? Let's say 4, 5, and 10, right? Okay, so these are our numbers. Oops. Well, what does that mean? That means that, I mean, we could just even write this out, right? So 4, we have 8, we have 12, we have 16, we have 20, 24, 28, 32, that's where I'll stop. 5, 10, 15, 20, 25, 30, 35, right? And then 10, 20, 30, 40, 50, 60. I guess actually 5 and 10 is a little bit bad, so let me just change this to, 12 is not great either. How do I do it? Let's just say 14, I don't know. 42, was it 56, and then 70, I don't know, right? And so what do we know here, right? With the same idea as the circles, let's just say how many numbers do we care for under, say, 100, right? Well, 100 we have how many numbers of 4s? We have 25 multiples of 4s, right? And we have 20 multiples of 5s, and we have, what is that, 7? Is it 7 or 6? I don't know. No, it should be 7. 7 multiples of 14, right? Okay, but of course, if we just add them up, 25 plus 20 plus 7, that's going to be 52, right? That's too many, right? Because as you can see, 20 is repeated. 20 is repeated. 70 and, well, from the 5 side, 70 and 50, 70 and 70 on the 5 side will repeat, and also 4 and 28 and 28 will repeat, right? Okay, and then another one that maybe will repeat is like 140, but we only up to 100, right? So then now we want to remove the things that we double counted, right? So we have to subtract. How many numbers are there for 4 that has both 4 and 5 as an overlap? Well, the greatest what's it called? The lowest common multiple of 4 and 5 is 20. So how many times does 20 or multiples of 20 appear? Well, 5 times, right? So you have minus 5, and then let's repeat this for 4 and 14. It's going to be 28, so then that's 3 under 100. And then the last one is 5 and 14, which we said is, I think it's 70. Is that right? So there's just 1, right? So then now it's 52 minus, what is this, 9? So it's going to be 43, right? But then now we subtracted too much. We actually didn't, because I made a poor example here. But yeah, but because the number that one is 140, because here, let's put, I messed up, but let's pretend this is 150 for a second, and then now you have dot 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 dot, you have 140, dot 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 dot, you have 140, dot dot dot, you have 140, right? And then with these numbers, remember, we add up all the 4s plus 5s plus 14s is equal to some number, and then we subtract 4 and 5s, right, which is 20, minus 5 and 14s, right, which is, what was that, 70 again, right? And then 4 and 14, which is 28, right? So we subtract these, but for the number 140, we subtracted here, here, and here. And so then now, but we only overlapped it twice, right? Remember, in the original thing, we have 140 appears 3 times, and here 140 also, we subtracted 140 3 times, so that means that we have to add it back in. So then now we have to add in back in 4 and 5 and 14, right? So that's basically the idea. As a visualization, I didn't go that much details into this and the proofs, and I think the visualization hopefully helps a little bit with the circles. But yeah, And then now we'll just go to the implementation. Again, if you want a deeper dive, this is what you would Google for. And they're probably better graphics than what I'm just giving you here in, in like 10 minutes, right? This is meant to be just, a little bit of an overview. But yeah, the idea, so using this, here we now using this formula or this idea, for a given number, we're able to say, okay, so let's just say we have f of some number, which gives us some other number of count of multiples under x, right, or whatever, right? Or what's it called? Number of, multiple, distinct multiples under x, or under or equal to, less than or equal to, right? So then now, given this, to get k, all we have to do is binary search on this number, because basically the kth smallest number, I think it's the kth smallest number, right? Yeah, is just equal to a number x, where f of x is equal to count of distinct multiples with exactly k number, right? K numbers. So that's basically the idea. I don't know why my binary search is disjointed, but okay. So I'm gonna look at the binary search first. I just chose a big. I actually should have. I think I did the math right on this one, but I chose a bigger number just in case anyway. But yeah, this is binary search. This good function for the binary search, as we always talk about, is let me say, return true if there are k or less or fewer multiples of coins under x. Under x, right? Or less than equal to, you want to say. And this is how I do it. I did it with a Bitmask thing, but the idea is that you can also do it with recursion as well. Just a way quick thing about Bitmask is that the idea behind the Bitmask is that, okay, the first number is going to be 0, the next is going to be 001, right? Something like this. Right, and then you have, and the idea here is that now you have all these bitmasks. You can represent this. You can look at the zeros as don't. Look at the zeros as don't count it, and ones as counting it. And then for example, if you have 3 numbers, like in this case. Let me put up there then. Let me just rewrite it. Let's say we have 3 numbers, then your bitmask will look like this, right? So that's the 8 possibilities. Zeros we don't care for because it doesn't do anything. Use 0 numbers. And then here, maybe the first column or the last column, if you want to call it that, it's going to be 4. The second one is going to be for 5. And the first one is going to be 14. It doesn't squeeze in. Sorry, all right? Look. All right? So, yeah. So then here, that means that use multiples of 4 only. Use multiples of 5 only. Use multiples of 4 and 5, which is 20, right? This is use multiples of 14. This is use multiples of 4 and 14, which is 28, right? Use multiples of 5 and 14, which is 70, I guess. And then use multiples of 4, 5, and 14, which is, again, is 140, right? So that's basically why I have bitmask here, and if from that context it makes sense. And here I thought it was GCD. If you watch me solve it live, I actually messed this up like a few times because I haven't done this in a while. But eventually I did get it with LCM, and that's how you can do it with, like I said, least common multiple, and just counting the number of counts. Notice that with the principle of inclusion-exclusion, exclusion, not excursion, is that you subtract the even number, the things that contain the even numbers, and you add back the ones with the odd numbers, the odd counts, and basically that's how I did it here. So the total is going to be just, and this is very simple, right? If you have a multiple that is g, this is just x divided by g is the number of numbers under x. And then here, if it's odd, if this is even, then you have negative, and then you just sum it together. And then now, after you sum it all together with this principle of inclusion-exclusion, check if it's less than or equal to k, or greater than or equal to k, and that's pretty much it. I'm going to delete this so that you could see most of the code closer. But yeah. I really should have gotten this. I'm pretty rusty on this one. I got this one in about 10 minutes. I should have been much faster on it. I knew how to do it immediately, but I don't know, implementation wise, which would be a theme when you go to watch Q4. But yeah, that's pretty much it. Yeah, so what is complexity here? Well, this binary search is going to be on the number of bits. We have 10 to the 9, 2 times 10 to the 9, which I guess coin only goes up to 25. I actually missed this, but I mean, I think I remember this, but yeah. So then now you have 25 to the 15, roughly speaking, which is actually a big number. I mean, GC, yeah, I don't know. Maybe I should have gotten a bigger number, but in any case, let's just say it's 2 to the, like, even if you do like 2 to the 60 or something like this, that means that this only does like 60 loops, right? So you'll be fine either way. If you want to pick a bigger number, it should be okay. So this does like 60 loop, and each loop does this principle of, you can see that this Bitmask is inclusion-exclusion, and this inclusion-exclusion is 2 to the n, but n is only 15, right? The word is 2 to the 15. 2 to the 15 is 32,000. So one loop of this is 2 to the n. 2 to the n times n. So because of the inner loop, right? So then it's that times the number of bits, which is what we have here. And that's pretty much it. This is our complexity, given that B is like, I don't know, 60, say, as an upper bound. I don't know. I'm lazy to calculate it out this time. And n is 15. 2 to the n is 15. So, yeah, what's that? 32,000 times 15 is like, 400,000 times 60. It should be fast enough. And yeah, and that's pretty much all I have for this one. Let me know what you think, and you can watch me solve it live in the contest now. I rushed at this one a little bit, to be honest, but still. Okay. Dumb mistake. Practice, Larry. Alright. Cave smallest amount that could be. Okay. K is pretty big. Oh, is it 2 hard problems? Is that right? Okay, so maybe we'll make up the silly mistake, but that's not great still. But smallest unique amount, or no? It's okay. No, it's not unique, right? So okay. No, this is fine. It's not that bad. People haven't gotten it yet. Okay, fine. It's just inclusion-exclusion. Okay, yeah. K is whatever. Is 0 one of them? No. Okay, fine. That penalty is gonna kill, like, annoy me though. But if this is good, that means that this is enough. K or greater, so then we subtract. Exactly K, right? Okay, fine. I think that's good, maybe. Click X, right? What a dumb mistake though, right? That should not have been. Hopefully 2 hard prompts will let me make up some time, but still. How do I want to write this? Yeah, okay, fine. Focus, Larry. What are you doing? You know how to do this. Just do it. I haven't done this in a while, though, to be honest. Okay, still. Yep. I believe in you, Larry. They're all unique. Pairwise distinct. What does pairwise distinct mean? Are they just unique? I mean, I guess so, but that's just a weird way of saying it. Okay, fine. Oh no, this is not right. Okay. Yeah. If there's 1, there's 2, and you yeah, right. So it's 2 you subtract. So then now. Right. Hey, really? That means I messed up something, but let me double check. Or total is wrong, so that's why. Oh, what is this? X? No, X is right. Did I mess something else up? Why is this so weird? Total count. Am I messed up inclusion-exclusion? I guess so. Alright, so let's say I have 10. This is going to be 3 plus. What am I doing wrong? This should be right. But maybe not. Because I'm giving zeros for everything. Oh, I'm missing the. No. Okay, so you want to count. Am I missing the. Maybe I got the signs wrong? No? Why am I so dumb today? Okay, so count, total, count is 0. Zero objects, okay, that's fine. 1 is 3. Now let's try I. Did I mess up some other stuff? So I is 1. That seems right. Oh no, this is the way I'm doing it is dumb. What I need is, oh yeah. What am I doing? Is it GCD or? This is not right, but that's fine. Oh man, I am just bad at this. Is it GCD? I can fix this. Yeah, it's just GCD, right? Okay. Was it nums or coins? J if G is none. Okay, and then now is this. Okay. Int. Oh, if this is none. Well, it has no numbers, so there should be just one. I'm just being dumb on this one, actually. Is the answer 20? No, it's still 1 for 20, so I mean, it should be bigger, but okay. All right, 3. There's one number, that's right. 1 and 2 is -3, is that right? No. It's not GCT, it's LCM. Yeah, what am I doing? I am so bad today. Okay. Don't submit, don't submit, don't submit. You have to change the constant, Larry. I have to say it out loud because I forget. Okay. Give it a submit. Okay. Whew, how many people got that one? 31. Yeah. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this explanation, this problem, this contest, everything in between. Stay good, stay healthy to good mental health. I'll see y'all later. Take care. Bye-bye.